Okay, so we're going to show that this union of pseudospheres is shellable. The dimension part is necessary but basically trivial. So what we need to do now is find our Schelling order. So we know that a single pseudosphere is shellable, but we don't know much about the unions. So here we have our, this is our sigma that we're working on, and this is the face tau. And this is an example of a facet of the pseudosphere. So tau is the red simplex, and each of the vertices in tau is decorated with a tau sub I, which is in this range here. So this is kind of a generic facet of the pseudospheres. And so in order to order these things, I'm going to give each one a signature. So the signature is going to be, well, tau sub 0 is the label on p sub 0. There's no label on p sub 1 because it's not part of tau, so I'm going to put a bottom here, and so on. So this string consisting of either bottom or face of sigma, we'll call that the signature. We're going to do lexicographic ordering on signatures, because shellability is all about finding these total orders with magical properties. We're going to order these things in this way. So we'll do lexicographic order where bottom is maximal and sigma is minimal. Lexicographic order means given two of these things, I look at the first two symbols, the next two symbols, and so on. I find the first place where they differ, and then I look at the order of those two symbols, and that's the order of the actual object. There's lots of other ways to, other orders you could choose, other ways to do this, but this one seems to be the most convenient one that we found. Okay, so this proof of shellability is going to look exactly like the other proofs of shellability, except for the details. So we're given phi sub j in the Schelling order, and phi sub I, which precedes it in the Schelling order. And we're going to do this lexicographic comparison where we run down looking at the symbols. And let's say that the elf symbol here is the first one where they differ. So L is the index of the first difference. And what we know is because phi sub I is less than phi sub j by hypothesis in the Schelling order, it must be the case that rho sub L, the component of phi sub I, is less than tau sub L, the component of phi sub j. Oh, because we're ordering them lexicographically by these symbols. So we start at the beginning. So I say pick an arbitrary phi sub j, and then for any phi sub I that precedes it, we're going to line up their signatures and then run down until we find the first place where they differ. And because by hypothesis this precedes phi I precedes phi j in the Schelling order, it must be the case that this is less than that in the. Oh, they're comparable because we have a total order on them, which is we have the face order. If they're both simplexes, then it's the face order. And if one of them is the bottom symbol, then bottom is higher than any face.
The thing is that this order that you use at the top, this is the special Schelling order.
This order here is the lexicographic order, and I'm going to prove it's a Schelling order.
Yeah, but this is the lexicographic order.
Yeah.
This is not ordered by containment or anything. This is
No.
just the order that you have defined before.
Yeah. So what I'm going to do is I've defined this lexicographic order, and I'm going to prove that this is, in fact, a Schelling order.
Yeah. But this is just a total order that you've just defined, and you can throw. So it's total by definition.
It's total by construction, yeah. And the thing about shellability is that there may be many different orders that all prove that something is shellable, so it's not unique. And so you can choose whichever one is most convenient for proofs. So what I did here was I defined this total order on on facets. So this is a facet of this pseudosphere, which is a subcomplex of the whole thing. And what I did was I defined a signature by going around the vertices in order and writing down the label that you find, or bottom if that's not there. So every face here has has n+1 symbols. And I'm going to use this to define a total order. So the definition is that the label here is a face of sigma, and we have this face ordering of sigma that we did with the bitmaps. So it almost doesn't matter what the order is as long as sigma itself is the minimal element, and then every face of it is higher. But the way we defined it is, I'll give you a bitmap where you have a 0 in position I if that vertex is present in the face, and 1 if it's absent. And then we do lexicographic order on the 0s and 1s, moving down until we find a difference, and then ordering them in that order. And so this is not a containment order. This is just this arbitrary 0, 1.
If we change the label of each vertex, then that would be a different lexicographic order. So we are proving that given any lexicographic order, and
yeah.
That would be this order that we want.
I'm not sure that any lexicographic order works. I think a lot of orders work, but when we prove this is a Schelling order, we're really going to get down and take advantage of detailed properties of this particular labeling. So I don't know whether any order would work, but certainly the specific one that we've constructed should work.
So it goes like 0, 1 bottom?
Yeah, so each of these has its own bitmap, has its own signature, and so we compare those by signature. And then we have a larger, so that we use that to compare these labels here. And then we have a signature for this whole thing, which is just the list of labels with the bottom in here, where bottom is higher than anything else. And these definitions are sort of arbitrary, in the sense that there are a lot of different ways this could have been done. But of all the ways I tried, this one fit on the fewest number of slides. So we have this order, and then what I want to show is the Schelling property that if I take phi sub j and an earlier phi sub I, then I can construct a phi sub k with the maximal and absorbing properties and so on. So what we do is we take phi sub I, phi sub j, we find the first place where they're different here. And what do we know? Well, we know that it must be the case that the label of phi sub I, which is written rho here, it's got to be less in this ordering than tau sub L. And so what do we know? Well, we know that tau sub L is not equal to sigma, because sigma is minimal. So the ordering is set up so that the whole thing, sigma, is the minimum set, and then each of its faces are greater than it. Yeah?
Can't it be that the first index is the bottom and the simplex? I mean, tau L is bottom?
Yeah, tau could be bottom.
Okay,
Yeah, so that'll be one of the cases that we'll look at later. So tau could be bottom, or tau could be a simplex, but if it's a simplex, we know it's not sigma, because sigma is minimal in the order the way we've set it up. So we're taking advantage of the specific structure of the order that we set up. Because this is just going to be a case analysis of all the things rho and tau could be. So it's not sigma because sigma is minimal. Rho isn't bottom because bottom is maximal. So we're doing this here to cut down on the number of cases to consider. Okay, so let's look at one case where tau is not bottom. So remember, tau is not sigma, but it could be bottom. So the first case is, let's assume it's not bottom, and then we'll consider the case where it is bottom. So if tau isn't a bottom, then what I'll do is I'll take phi sub j, which has tau in there, and I'm going to replace tau with sigma. You know, the entire thing. So that says that suppose it actually, instead of hearing from tau, it heard from everyone. And the signature, so we're going to define phi sub k, we can define it by its signature, because if you know its signature, then you can reconstruct the complex and vice versa. So what we'll say is that phi sub k has a property that agrees with phi sub j, except at L, where it's sigma. So, you know, this is just a LaTeX-y way of saying that we replace the one vertex here. So we replace this, and then we get phi k, where we take out tau and we put in sigma. Then we need to check, first of all, that the simplex, the facet that we've defined, really is in the complex. But that's true because sigma is certainly in between tau and sigma, by definition, because it's inclusive. So we know that we're OK. How do we know that phi of k is less than phi of j? Well, because sigma is less.
It's RA or should be RS?
Oh, this should be RS, yeah. Yeah, that's a typo. And there's some color typos also. So here we want to show this is maximal and absorbing, and that just follows because we've only changed one vertex. So that's one case. The other case is suppose tau sub L is bottom. Okay, then notice that phi j and phi I have the same dimension. So it must be the case that if we have bottom here and something here, then there must be a later index where it's the other way around. Because the adversary always fails exactly k in every round. So you start out with sigma, and then the non-faulty processes are that number minus some set k. So that because the adversary always leaves the same number of non-faulty processes in every round, it must be the case that if you have two facets, they have the same dimension. So it goes back to the fact that the adversary always fails exactly k. If the adversary could fail a variable number of processes, then this wouldn't work. And surprisingly, that's going to come up when we talk about other models later on. But in this model, it's easy because the adversary is very precisely fails k processes. A compulsive adversary. Yeah. So what we do is we construct phi k by taking phi j, putting sigma here, and putting bottom there. And this is the what happens if you write it out. And then the rest is just checking that this actually works. So we want to how do we know that this is actually in the complex? Well, the phi I is in one of these pseudospheres for some tau sub I, and phi j is in the pseudosphere for tau sub j. And so we define t sub k to take tj and add one thing and move the other, and then we can check that, in fact, everything works out.
Did you
Yeah.
mean tau sigma and tau m in the
Oh, no, these are different.
when you say replace L with
Replace, yeah, tau sub L. Yeah, that's right. That should be tau sub L rather than L.
and tau m?
Or it should be replace position L, but it should be something, should be one or the other.
What are SL and SM?
Oh, vertices. So this is whatever the vertex is with index L, and this is whatever the vertex is with index M. So we throw away one vertex and we stuff in another, and then we check that in fact this simplex that we this phi sub k that we constructed lives inside one of the pseudospheres that lives inside the protocol complex. So again, this is all sort of detail checking. How do we know it's less? Well, if we do the comparison here, then we know that sigma is less than bottom. So, and that's the first symbol where they're different. So we're okay. How do we know that it's minus 1? Well, if we look at the three phi I, phi j, and phi k, then the only vertex that's in phi j but not in phi k is also not in phi I. So that means that the actually, yeah. So that also says that the intersection is absorbing, which it doesn't say on the slide, but that's the what it should have said. Okay, so that's so what we did there was we just said, well, here is a Schelling order that we came up with through a process of kind of mystic insight, and then we just go through and check and make sure the Schelling order actually works. And this is characteristic of most of what we're doing is we discover what the complex looks like, and then say what would be a good Schelling order to impose on this. You think of one, and then you check that it works. You know, there isn't any magical way of generating a Schelling order from the complex. In fact, in earlier versions of the original paper, we had used a different Schelling order. Okay, so what that says, so we just proved this theorem about the one-round operator. We didn't need to talk about multiple rounds, but because we have our theorem that says you can compose these things, so it says that the one-round operator is shellable of dimension k minus the codimension, and that's what we've proved. What are the consequences? Well, corollary is that there's no synchronous message passing protocol for k-set agreement in fewer than this number of rounds. So we can fail any C-1 processes, because if we had a set of C-1 processes where we couldn't fail them all, then we would have a core of size C-1, which contradicts our assumption. So because we can fail any set of C-1 processes, the adversary fails them k at a time. So this is the number of rounds you can keep things going. So an adversary with minimum core size C, you can prevent k-set agreement for this many rounds.
What happens when n is not larger than 2k?
Oh, I don't know. No, this is.
Because for asynchrony, this kind of sounds natural for message passing.
Yeah, yeah. Yes, so what happens? I think you're getting a lot of, that basically it says you can only run for one round, right? Because the, because, let's see. Yeah, because if n is smaller than 2k, then that means that if you fail a k, then you have less than k left. So that means that the adversary can fail lots and lots of processes, and it can prevent you from doing things for one round, but at that point it's sort of killed everyone and then can't do much more. So again, this bound is tight, and let me show you. I'll show you how to do this with an example. Let's say we have 5 processes and k is 2. So we line them all up, and then let's say we have a core of 4 processes. So these processes have the property that they can't all fail.
That's a quad core.
A quad core, yeah. Sounds like an Audi model. And so we divide them up into teams of C divided by K. So we have K different teams. And then what they do is each one of them can do consensus in ceiling of C over K rounds individually, just talking to themselves. And then when they're done, they tell the others. And so that's a tight bound. Okay, so that's, so we've gone from asynchronous message passing to synchronous message passing. And the next natural step is asynchronous read-write memory. And let's see. Yeah.
What happens if you put the row bound when this is exactly k? What happens if we know that it's less or equal to k?
What's exactly k?
You say that the adversary fails exactly k.
Yeah.
And what happens if we know that it's less, smaller, equal or less?
Oh, so if it's smaller than k, then I think then your adversary, if the adversary fails exactly k minus 1, then it will keep it k minus 1 connected. So that's simply the adversary. At that point, if the adversary fails fewer processes, then it doesn't stay connected. And if it fails more processes, it stays connected, but then the adversary can't keep going as long because it's it's killing processes too quickly. So it can only, so the number of rounds is smaller.
So if it fails less, you don't have the lower bound?
If it fails less, then you don't have the lower bound, yeah.
But it seems easier if less fails.
No, the adversary is trying to create confusion. And every time the adversary fails a process, that process can either send or not send messages to everyone, which means that everybody's views of the world can be slightly different. So the more the adversary can fail in a round, the greater the confusion it can create. And so the nice thing about the asynchronous model is it doesn't have to fail, it can just delay processes to create the confusion. But here, the adversary, if it wants to create confusion, has to kill processes, which you can only do once. And then, so if it kills too many, then the computation is too short. If it kills too few, then the computation isn't connected enough. So this is kind of a local optimum for an adversary. And the fact that the bound is tight says that in some sense the adversary can't do any better than this.
But if it kills no processes, then it's easy.
Oh, if it kills no processes, then everybody instantly knows what everyone else's state is, and you become disconnected after one round. Because then if there's one execution where I have 0 and I don't fail, then I tell everyone 0. And if there's another execution where I have 1, I tell everyone. And then these two things become disconnected because suddenly everybody knows 0 or everyone knows 1. And so it's only the fact that I can create failures that creates this ambiguity where I can't tell what the original states were. Okay, so I think, so I'm going to start this, but I'm not going to try to finish it. I'll give you kind of an overview, and then we'll review it again next week. So this is read-write memory. And this is asynchronous. So once again, the adversary is not going to fail anybody. Instead, it's just going to delay, it's going to create confusion by delaying processes rather than failing them. So in each round, each process is going to write and then take a snapshot. So writing is atomic, and taking a snapshot of memory is atomic, but these two steps are not done atomically, in the sense that a process can write, it can go hang out on the beach, have dinner, come back, and then do the snapshot. And
How long will we be at the beach?
we don't know. So it could be, what could happen is that I could do a write, and then everyone else could do their writes, and I come back and I see what everyone did. Or it could be that I had an espresso before doing it, so I wrote, and then I took a snapshot immediately, and I see my write and everyone's earlier writes, but not afterwards. And in fact, it's this gap between when you write and take the snapshot that's going to give us all the variability that we need to construct the complex. If you could guarantee that the write happened immediately after the snapshot, then you'd have what's called the immediate snapshot model, which is slightly different. This is a more general model. Turns out the two are equivalent, but we won't prove that. So this is not immediate snapshot. So here's a way to think about that. So here we have time, and there's a write order, so that every process writes once. This is a single round. You write once, you take a snapshot, that's it for the round. then you can go on and you can do it again on a clean piece of memory for the next round. So there's write order in which all the processes, each one writes. And we'll assume that they're writing into separate pieces of memory so they're not obliterating each other. And then there's a set of possible snapshot orders. So we know that yellow here could do a snapshot immediately after it wrote. It could take a small chodesh and read after blue, or it could take a French-style vacation and go away for a month and then come back and read after everyone is finished. And then blue would come along, and the only constraint is that you have to read after your own write, but you could read anyone else's. So these are kind of the degrees of freedom that the adversary has. And so we're going to look at all of them, rolled up into a simplicial complex. So the rule is every process has to see its own write, and maybe it later writes. And these things can happen independently. They don't have to, the order in which they do the snapshots doesn't have to be the same order that they wrote. But the snapshots are ordered by inclusion, so that a later snapshot sees a superset of what an earlier snapshot sees. So what happens is that here, for example, yellow might see only itself. Here, yellow, you might see yellow and blue. And here you might see all of them. So the possible things that yellow can see are a sequence of faces of sigma, ordered by inclusion. So before, when we were talking about everything between tau and sigma, these were not ordered by inclusion. Everything had to have tau and to be contained in sigma, but there was a partial order in the middle. Here, however, because it's a snapshot, everything is totally ordered. And so we'll call this a survivor chain. So what happens is that you have to see a survivor set. But the other things you could see are, or you could see everything. But all the possibilities, once having fixed the right order, all the possibilities are just prefixes of the right order. So I'm assuming here that we fixed the right order, and now we're looking at all the possible snapshots. And so we'll say all the survivor sets of sigma will denote by sigma with a bar over it, just because it looks kind of cool. So that's a notation for this chain, this sequence of faces ordered by inclusion. And we'll call chains of sigma the set of all chains. So we'll say that we use subscript I to say, look at the suffix of the chain that contains pi. Because if you're pi, then you have to see your own update, but you might also see anything in the chain that comes afterwards. So
the longest suffix containing pi.
Yeah. So here's sigma bar, and there's a sigma bar sub 2, because it's where 2 is red. And there's a sigma bar sub 1 and a sigma bar 0. So that's just the notation that we're using. Okay, so for each execution, what happens is every vertex in sigma, so there are no failures, so everything is over sigma. So what happens is you pick some element of the survivor chain containing yourself. So if you're the ith vertex, then again, we have the right order fixed. You go to where you wrote, and then you pick some point after that. And again, this is pseudosphere because everybody can independently choose which one they want to see. There's no dependencies among them. And then we take the union of this over all the chains. So again, the one-round operator is a union of pseudospheres. So what I'll do next time is we take the union is show that this is actually shellable also. So we're going to do yet another shellability proof, which again looks sort of like the ones we did, except that the technical details are going to be different because the complex is different, and the orders are different, and so on. But the point that I want to kind of emphasize is that there's very much a kind of common structure to all of these things. You know, the proof is the same going down until you start talking about the actual orders and the actual simplexes. Then it becomes model specific. But this is part of the program where we want to kind of prove general theorems and keep things as general as possible until we get to the very bottom level. And then we say, okay, because of the way the model is set up, we build things in this way. And so this is why we're, you know, this is the closest we can get to a kind of grand unified theory of set agreement in round by round executions. Okay, so we'll do that next time.